Hi folks, in this tutorial we'll try to determine how the atomic radii of elements change as you move across a period, of course in the periodic table of elements from left to right. To do this, we'll be using the atoms of the elements beryllium, boron, carbon and nitrogen from period 2. The atomic radius of any element is determined by how forceful the positive nucleus of an atom is able to attract the electrons towards itself. To help us know the relative radii of these elements, it is important for us to study the famous Coulomb's law. French physicist Charles Augustin de Coulomb formulated a law that governs the attractive forces between oppositely charged objects, such as happens between the positively charged nucleus and the electrons around it. To investigate Coulomb's law, we'll use magnetic forces to represent electrical forces, since magnetic forces are very similar to electrical forces. We'll first investigate how the magnitude of the opposite charges affects the force of attraction between the objects. To do this, we'll use two sets of magnets, a weak pair of magnets and a strong pair. We'll use the north pole of one magnet to represent negative charges and the south pole of another magnet to represent positive charges. Then what we'll do, we'll bring these together and then monitor the force of attraction between them. All right. So these here are a pair of weak magnets. And obviously they will represent relatively small number of positive and negative charges. Here's your north pole, and we shall assume that that represents a certain magnitude of negative charges, and the south pole here represents a certain magnitude of positive charges. So we'll now bring these together and try to monitor by looking at the way the magnets move, how forceful they attract each other. So here is the magnet, there's a south pole here, and this is my north pole here. I'm bringing this together here, and we look. So you can see that there's a certain force of attraction between these. I should repeat that for you to see more clearly. Okay, so here's it. Okay, now we shall replace these magnets here by ones that are stronger. And again, because they're stronger magnets, we will say that they represent greater magnitude of positive and negative charges. So now we'll monitor the force of attraction between these two strong magnets here. So that's the north pole here, this is the south pole here. That represents a large number of negative charges compared to the one before. And this one here represents a larger number of positive charges compared with that before. So let's monitor the force of attraction. You can see that? Definitely you can see that the force of attraction between these two magnets here is much greater than what you had there before. So this is the point that Coulomb is making in terms of the force of attraction as far as the magnitude of the charges are concerned. Coulomb is saying that the force F is directly proportional to the magnitude of the charges. We call it Q1 and Q2. Q1 represents the number of negative charges and Q2 the number of positive charges. The force of attraction is proportional to the product of the magnitude of these two charges here, all right? Next thing we'll do is to find out how distance affects the force of attraction. We'll use these two magnets here and place them at different distances from each other. So them close. First of all, we put them close together and monitor the force. So that's it. Okay. Now what we'll do, we'll move the magnets farther away and monitor the force of attraction between them. Look. See that? You can see that the force of attraction is much weaker than that before. So repeat it again. Close together. That's how strong the force was. Okay. Farther away, weaker force. So What Coulomb is saying here is that the force of attraction is not directly proportional to the distance, but is inversely proportional to the distance squared. So putting all of this together here, putting these two factors together, the factor of magnitude of the charges and the distance between them, so Q1 times Q2, you put that over d squared here, and this represents Coulomb's law. What you've done across here is this. For each of those atoms here, we have drawn the Bohr-Rutherford diagrams. If you observe the Bohr-Rutherford diagrams as they are drawn there, you see that the nucleus of beryllium has 4 positive charges. That's because it has 4 protons. Boron has 5 protons, 5 positive charges, carbon 6, and nitrogen 7. Notice how we have not indicated the neutrons in the nuclei here. We did not include neutrons in the nucleus when you're doing these types of diagrams where you want to determine the atomic radii, because neutrons being neutral in nature do not affect the atomic radius of any atom in any effective way. That's why they're not shown there. Okay. Now I want you to look at these diagrams here and see if you can detect any difference between the ones at the top and the ones at the bottom. Any difference? Yes, you should be able to see that I have reduced the nuclear charge in every case by 2. What else did you see? You're not seeing these 3 electrons here. You're not seeing the inner shell electrons. Why do you think I did that? You see, the K shell electrons are very close to the nucleus. And what is happening there is because these 2 electrons are so close to the protons in the nucleus, we say that they neutralize 2 protons. Or alternatively, we can say that 2 of those protons neutralize those 3 electrons. Or generally speaking, we can say that they mutually neutralize each other. You're not seeing them there. That doesn't mean that they do not exist, but they nullify each other's effect. That is why we're not showing them. So what is left in each of these nuclei here is what is called the effective nuclear charge. Effectively, what is left is 2 positives there, 3 positives there, 4 positives there, and 5 positives there. One point I want to talk to you about. As these diagrams appear there, one will be made to feel that the atom is a 2-dimensional structure. Indeed, it is not so. Every atom is 3-dimensional in nature. You see, the electrons around the nucleus of an atom are not localized. They're zipping with lightning speed on or about the nucleus of the atom. And wherever they go, they need their negative influence there. It's like I have a fireball, right? And this fireball is moving around with lightning speed, and it demarcates a volume of space that is spherical in which it moves. How do you think that sphere will feel? The entire sphere will feel hot. Similarly, as electrons zip around on or about the nucleus of an atom, wherever they go, they leave that negative characteristic that we call a negative cloud. So an atom really has a central nucleus here that is surrounded by what we call a negative cloud of electron. This electron cloud can expand and contract. The degree of contraction, of course, depends on how strongly the nuclei of the atom is attracting this negative cloud. So it's like this here. Let's say that this model here represents an atom, right? Right now you can see this atom has a big radius here, right? If now the nuclear charge increases, what do you think will happen? This thing will start to contract like that, okay? And the radius becomes smaller and smaller. So the electron cloud can expand and contract like that. It will contract depending on the force of attraction between it and the positively charged nucleus. In this second set of diagrams here, we are seeing that the nucleus of beryllium, with its two positive charges, is attracting two outer electrons here. Boron with three positive charges, attracting three electrons. Carbon with four positive charges, attracting four electrons. And nitrogen with five positive charges, attracting five electrons. As a reference point, we have drawn the atomic radii of all of these atoms here to be the same. We're assuming now that the outer electrons in every case are equidistant from their nuclei. Okay? We'll now apply Coulomb's law to help us determine which one of these nuclei here will attract the electron cloud closer to itself. The one that attracts the electron cloud closest to itself will have the smallest atomic radius, whereas the one that barely attracts the electron cloud to itself will have the largest one. So to figure out that, we have to apply Coulomb's law. If we apply Coulomb's law in these figures here, we can have these values here. For beryllium, the force of attraction is proportional to 2 times 2, because these are magnitude of the charges on the electron, and that is the magnitude of the charge on the protons here. We have 2 negative charges due to 2 electrons, 2 positive charges due to 2 protons. In boron, we have 3 negative charges times 3 positive charges. Carbon, 4 negative charges times 4 positive charges. Nitrogen, 5 negative times 5 positive. Because we said that the electrons are equidistant from the nucleus of the atoms, then D squared does not come into play here because D is the same in every case. So what we have here, we'll say we have 4 units of attraction between the electrons of beryllium and its nucleus. Here we have 9 units of attraction between the electrons of boron and its nucleus, 16 units of attraction between the electrons of carbon and its nucleus, 25 units of attraction between electrons of nitrogen and its nucleus. Based on these results here, in which direction do you think the force of the nuclei on the outer electrons will get bigger? You say in that direction or in this direction? Obviously, when you look at these forces here, you can see that beryllium will have the least force here, and nitrogen will have the greatest force. Therefore, the force of attraction of the nuclei on their outer electron will be in that direction. How do you think that the atomic radii will look like? Obviously, as you move in that direction there, the atomic radii will get smaller and smaller, because as you move in that direction there, the effective nuclear charge gets bigger and bigger and is able to attract the electron closer to its nucleus. This figure here tries to depict how the atomic radii will change as you move from left to right across the period 2 of the periodic table of elements. Finally, I've used these styrofoam balls and marbles here to depict the change in atomic radii as they move from left to right across a period in the periodic table of elements, and specifically for those 4 different elements there. This here is beryllium, there's boron, there's carbon, and there's nitrogen there. 2 things I want to bring to your attention is this. As you move from left to right, the atoms are becoming more massive. Beryllium has a relative atomic mass of 9.01 atomic units. Boron, 10.081 atomic units, carbon 12.01 atomic units, and nitrogen 14.01 atomic units. So the atoms are becoming more massive in that direction, but they're becoming smaller and smaller. What do you think will happen with the densities of these atoms? Obviously, the densities will increase in that direction. The atoms become denser as you move in that direction. So you expect nitrogen to have the greatest density than all of these here. Beryllium will have the least density. Second point is this. How do you think the ionization energy will change? Recall that ionization energy is the amount of energy it requires to remove an outer electron from an atom in its gaseous state. In which case you think the ionization energy will increase? If you say the ionization energies will increase in that direction, you're right. Why? Because as you move from left to right, the effective nuclear charges increase. And not only that, you can see the atomic radii are also getting smaller and smaller. Therefore, as you move from left to right, the outer electron is held stronger and stronger in that direction. So in this case, it will be held most strongly by nitrogen. And then as you move in this direction, and that's why nitrogen will have the greatest ionization energy, and this one here will have the least ionization energy. I hope that all that we've done today was able to make you understand how the atomic radii of atoms change as you move from left to right of a period in the periodic table of elements, and how also the densities of these atoms change and their ionization energy. Thank you.